Hello students, in this lecture we'll be discussing about uh, thermal barrier coatings. But in fact they're also called TBC. Now thermal barrier coatings are well used in gas turbine blades, and they are the adherent layer, so they actually act as an adhesive. So there is an adherent layer of a low thermal conducting material to a surface of internally cooled gas turbine blades. So the basic principle is that, or the basic mechanism is that there is a temperature drop can be introduced across this excess of layers. So temperature drop uh, can be introduced across this excess layer. So there is actually no CT mismatch. So mainly they are done to solve the problem of CTE mismatch between the two types of materials. So there is a thermal barrier which needs to be added as an extra layer to control this problem. So by having an extra layer, what it does is it results in a reduction in metal temperature components which is applied. So in other words, difference in reducing the difference between liquid CT mismatch means it is resulting in reduction in metal temperature components. So mainly these are a ceramic material, so it actually protects the metal from excess change in temperature. And temperature, due to this, there is a temperature drop, as already told, through this thermal barrier coating, and the temperature drop is around up to 170 degrees centigrade, and it also depends how much temperature drop will take place depending upon the thickness and the material used as TBC. So it's 170 degree for 150 micrometers for YSZ thermal barrier coatings, YZ stands for yttrium sulfide zirconia coatings. YZ. Now, coming to the other types of materials which can be used, or we discussed the type of materials which can be used as a TBC. So the first thing is, the very most common TBC used is CRAL. So where M can be nickel, it can be iron or cobalt, and these TBCs are also called bond coat. Now, the zirconia is a very integral part of any thermal barrier coating. So, ZrO2 zirconia. The zirconia has three different types of phases. It can be a monoclinic, or it can be a tetragonal, or it can even be cubic. So there is a phase change occurring in zirconia depending upon the conditions of the material. So if this phase change in zirconia occurs during its application even. Now, you need to improve the fuel efficiency of jet aircrafts. So that is the ultimate objective. Improve fuel efficiency of jet aircrafts. And also, you need to increase the operating conditions for turbine engine components. To increase operating conditions of turbine engine components. In fact, to actually improve the fuel efficiency only, we need to increase the operating conditions. And then, so basically, when we're talking about turbine engine components, we're mainly talking about the turbine blades. These are the main focused area of the components. Now, the metals used for making turbine blades are cobalt, nickel, and iron-based superalloys. Making turbine blades. And these superalloys have excellent bulk strength and ductility at elevated temperatures. They should have excellent bulk strength and ductility at elevated temperatures. At high temperatures. Now, so when we're taking the turbine blades to high temperature, there can be some high temperature degradation. Let's call it as HT degradation. So to protect or to prevent such HT degradation, the thermal barrier coatings are used. So the bond coat that we have recently discussed, it provides a glue layer. It's a glue layer between the metal and the outside protecting coating layer. So if you look into the structure of TBC, it's the metal used as in turbine blades, which needs to be protected from high temperature degradation, and so we are providing a TBC. Say, consider this as the TBC. This is the metal, the superalloy. Now, in between these, there should be a bond coat, which actually acts as a glue between these two components. So, bond coat we have previously discussed. Bond coat is MCRALY. And the TBC, most commercial, is yttrium stabilized zirconia. Yttrium is used, it protects the bond coat from accidents, and so it actually protects the bond coat from accidents, and also shifts the failure from metal bond coat to metal to the oxide layer. So basically, if you again draw the picture, this is the metal or superalloy, turbine, whatever you call it. This is the TBC, where we are using yttrium stabilized zirconia. That means basically it's an oxide. So what the yttrium, the role of yttrium is very important here. What yttrium will do, it will transfer any failure. Suppose a failure has taken place here between the metal, the superalloy junction and the bond coat junction. This is the bond coat. So what yttrium will do, it will shift the failure from this junction to this junction, to the oxide part. So I call it yttrium stabilized zirconia. It shifts failure from metal bond coat interface to bond coat to the oxide part. So the yttrium stabilized zirconia. Now, as we have said that due to application of this TBC, there is a temperature drop that is taking place. Now, this temperature drop, it reduces the oxidation rate of bond coat. So, another advantage is it reduces the oxidation resistance. also oxidation rate, not resistance, of the bond coat. So due to this, what happens is that there is a delay in failure of oxidation. So delay in failure by oxidation. And so this is the application of TBC. So it adds to the durability of the component. So durability and life of the component increases. Shoots up. Now, as I said that yttrium stabilized zirconia are used as a TBC. Now there is no single coating composition which will satisfy all the requirements. There are some multifunctional requirements of the for protection. So no single component coating meets all the requirements. So we have three separate layers of coating system. For TBC, sorry, first one is of course the TBC. Then we have bond coat, and then we have TBC. Now this TBC is likely to have a thermal expansion coefficient that differs from component to which it is applied. So the CTE thermal CT coefficient is of course different, and it accommodates thermal misfits. Now it is basically a porous columnar layer of say yttrium stabilized zirconia. Now this layer or the deposition of layer is usually done either by air plasma spray or it can be also done by electron beam evaporation, which is a PVD technique, physical vapor deposition technique. So the first layer is the TBC. So if you draw a diagram, so let's say this is the turbine plate. And a nickel based superalloy has been used here. an Ni super alloy. Then we have the oxidation resistant bond coat. Let's call it oxidation resistant bond coat. So this is the second layer, and lastly we have insulative TBC. Last layer, which is the TBC, it is a insulator. So this is the three systems. The first is the TBC. If you look in the opposite way, so this is your TBC first, second is your bond coat, and third is your turbine blade. So there are three layers, which makes the total component, total system. So one is TBC, two is the bond coat, and the third is the super alloy. So these three layers are used, and it helps to improve the efficiency of the turbine blade and its functioning. So fuel efficiency is also increased.